keep joining, and so we will start the event. So for today's event, as a guest speaker, we have Vishal Mourya. Vishal Mourya is the founder at Programmers Army. He is a president at CodeChef College chapter at Thakur College of Engineering, and also the Coding Club president, even that also Thakur College of Engineering. He is rated 6-star on hackerrank and also an Flutter developer and mean stack enthusiastic. Thank you so much, Vishal, for coming over here, and over to you. Now you can continue.
Yeah, thank you so much, Vaishnavi, for a very nice introduction. So, so let me just share my screen and we'll go on with the flow. Just let me know if it's visible. I guess it is visible, right? Is this any of you can
Yeah, it's
confirm?
visible.
Yeah, it's visible.
Yeah, thank you. So we'll be just like going on to some theory part. I know it's boring, but yeah, we have to cover some theory. Then we'll be just directly jumping into the implementation of how exactly the tree data structure is, implemented and how we use this particular tree data structure to solve various problems. And we'll be jumping on to like interview problems, which is the hot topic. Which in every interview, like if it's a high level interview, then you will be facing the problems from trees and graphs and DPs. So let's get started. So here I go. So first thing, what I would like to know is first I would like to analyze what type of actually the audience I'm facing today. So can you just type in the chat of the meet like what exactly while hearing this tree data structure or what exactly you have been known before, or how much you know tree data structures. Are you a totally beginner or you are an intermediate? So that I would have a grasp of how exactly what all things I like to like share, because if you are not a beginner, then it will be waste of time for you to like going through that things. So just type in the chat. I'll be just seeing that chat and letting me know that what you all guys know about tree data structure. So just quickly type in the chat. I'm waiting. So yeah, guys, you can just even unmute yourself and just say it. I guess like people are typing, so it's taking them time. I'll be just waiting for a minute and then I'll be continuing. So okay, Sanjay Shukla is telling his no like basics of trees. Okay, that's good. Anyone else would like to add anything? Just
Actually, see, we already have major chunk of first year rights and secondary rights in our event. So I think basics of knowledge and just a beginning of the knowledge of trees everyone have.
okay, so yeah, so I think yeah, we can just go ahead with the flow because actually the audience which I was expecting, this is the same. So let's move on with the flow which we will be discussing. So the flow for this presentation will be like we'll be just going on to some introduction to trees, which will be really very quick, and then we'll be like looking on to basic terminologies. After that, we'll be actually like diving into coding for how exactly tree data structure is implemented, how various traversals on trees are done, and then we'll be like moving on to solving the interview questions, or you can say the famous questions on trees. Or I'll be like showing you some websites. You can just after this session, you can just go on there and then practice various questions. So let's get started. So firstly, like this is the typical definition of tree, which is not quite good for beginner because let me just use my pen. Okay. Yeah. So if you can see, like as a beginner, when I also like went through this definition, it was not easy for me to digest. So we'll be just breaking out this definition and like we'll be understanding the actual thing what it is trying to say. So for the sake of like a tree data structure, this definition is what Wikipedia says. So this is what is it, but I'll not be explaining this. I'll be coming on to this in a few minutes, where I'll be like first glancing you through every detail of what is tree and like why we need tree, and then what all terminologies we use in tree. Then only like it will be more easier for you to grasp this. And yeah, so let's move on. So firstly, while anything exists in world of data structure and algorithm, then there is a reason behind their existence. So let's say you have a stack, you have a queue. Like people don't think while implementing them or while learning in the so-called semester of our engineering or any other course. So they just like implement these stuffs, and like it was written in book, so I wrote in my book and then just copied it and just passed out my exams. But in interview, what they want from your side is what exactly you understood from it. So recently I was having a talk with the guy who is just placed in Google. So what he was telling is, so he was telling you don't have to actually write the code. You have to first grasp the logic behind everything. Why that data structure is needed. Why that implementation is needed of that data structure. So yeah, so like we have this data structures as arrays, linked list, stack, queue, and other linear data structures are also present, but that stores data linearly. So what tree data structure do is it allow us to perform the operation dynamically, or you can say more appropriately, randomly. So in today's computation world, as you have seen while solving questions using array, let's take the basic example which all of us will be familiar with. So in arrays, what we usually have is we have a linear allocation of memory. So what that means is the memories will be allocated in the linear fashion. So whenever you are want something from the array, you just need to traverse that array, and then you'll be getting that thing. So this computes really a high computational power. So that in case if memory is not available in continuous fashion in for that particular amount of space you require, then your array will not be constructed in the memory. So that is all the basic drawback. So there's how the tree data structure comes into picture, and then we can just use it and can just play around it. So let's move on some basic terminologies of the tree data structure. So first is this root. So what exactly is this root is, let me just show you the diagram. Okay, so this is the basic typical tree. You can just focus on this diagram right here. I'll be going on to right side very soon. So this is the tree, the typical tree, which how it looks like. So actually it's the reverse of the tree, you can say, which exists in real world. So you can just see this is the root node. We can say this is a root node. So why this is root node? Because you can see we don't have any edges coming towards this node, okay, or any edges connected to this node right here. So because this node is the root node, so this is how root node is defined, the top node in the tree. So this is actually the root node of a tree. In every tree we have a root node. Root node is basically the identification of any tree. Whenever you will be given a problem to solve, the first and the important thing you'll be required is the pointer. In C and C++, we generally say this pointer, but in other languages, we also term it as a references. So you'll be given this pointer or references to the root node, and then you'll be asked to solve the problems based on that. So this is the root node, which is defined for this tree. Now moving on to next thing, this is the child, it's just a next node connected downwards. So what does that mean is, as this is the root node, so you can see we have this edges. So as you can see, this is the edge, and these are the nodes of this tree. So every tree will have these two basic components, the edge and the node. So one of the node will be the root node, and other nodes will be the child node. So I already told, this is a node, root node. So this node right here, or this node, or this node, or this node. So they are the, you can say, the child node of this root node. And if they are child, then we can say that if they are child, then the root node is parent of all these nodes. Now apart from this parent of this tree, there are more parents of this tree. If you can see, this node right here has two more children, like this the left children, and this the right children. So this child the child node of this parent node, which is the root node, has two more child nodes. So this node is also the parent of two nodes. So this is how a typical trees goes, and this is the hierarchical structure, you can say. As we see hierarchical structure in many organizations even. So starting from the students committees and faculties, and going on to head of departments and deans, and then finally reaching up to principal. And similarly, we see the hierarchical structure in family. We basically call this as a family tree. So let's say this is the grandfather, and then father, and then we. So this is how something like tree data structure follows. So moving on to next. So as I told, the parent is nothing but the converse notion of child. This basically means the parent will be having the child. So now what is this sibling? So this is interesting thing. So nodes with same parent. Let me just yeah. Let me just first erase this, and then I'll be just explaining. So while explaining these things, if anyone wants to ask anything, then they can just write in the chat. I'll be dealing with the doubts right there. I don't want anything to be left for the last as such, because the things will be clear right now, then it will be very good from my side and even from your side. Even if you're you can unmute yourself and just ask anything you would like to ask. So yeah, let us continue. Okay, so I was just explaining about siblings. So what is siblings? Like the node having the same child. So you can see this node right here, which is 2, okay, and this node right here, which is 3. So if you see, the parent for 2 is 1, okay, as like we discussed previously. So parent of 3 is 1. So you can say this two nodes have the same parent, so they are nothing but siblings. So this is how siblings are defined in a tree data structures. Now you can see this 4 and you can see this 5. They both are children of 2, but yeah, they both are children of 2, and they both have the same parent as 2, so they both are the siblings. So like I will like ask about you a question here. If you can ask, if you can answer or try to answer it. Like I said, the nodes having the same parent will be known as siblings. So if I ask you the sibling of 4 and 3, this 4, this node 4 and this node 3. So can you just answer any one of you, like what will be the, or who will be the sibling of this 4 and 3? Like, sorry, not sibling, the parent of, or you can say, what was that? Yeah, I like to ask this. Yeah. So, like, which node is the common parent of this 4 and 3? Can you all just answer this question?
One.
If,
One.
sorry. Yeah, so that's right. So that is nothing but the term which is in graph or tree. So it's ancestor, you can say this. Yeah. So ancestor. So they are known as ancestor. Like if two of the nodes or two of the childrens are having a common parent, so they are also termed as ancestors. So this is how like we basically deal with terms in trees data structure, and then we have this thing like leaf. So leaf are nothing but a node with no children. As we have like the node with no parent, we call this as a root node. So as you can see, there's two nodes here and the one node here, so they don't have any child, like they don't have further any child like this or like this. So they are basically the leaf nodes of the tree, so where basically our tree ends. So this is the end of the tree, you can imagine in that way, and this is the start of a tree. So we always start with root node and we just go to our leaf nodes by various paths and using this edges which they are connected through. We cannot directly jump to like 1 to 5 because we don't have a path from 1 to 5 directly. We like have to go through 2 and then we have to like go to 5. So this is how the actually the path tracing we do in like tree data structure. So moving on to like the right diagram which is shown here. Let me just erase this all. So like focusing on, mm, just a second, I just missed that. So focusing on this right diagram right here. So what this right diagram is trying to show is nothing but the height and depth of the tree. The H here stands for the height and the here stands for the depth. So how actually we calculate, or how actually we know that what is the height of the tree or what is the depth of that node is now what we'll be looking into. So let's say this is the root node, as I told, like this is the root node and this three are the child node for this tree, and this is the middle node. So you can see this node here, it is written as HS2 and D is 0. So let us first ignore that. So whenever we'll be like calculating the height, we'll be just starting with the leaf node. You can see this leaf node right here. So we tell they are at level 0. And then the nodes apart from like leaf nodes, one level up, they are at level 1. And this line, this here right here, they are at level 2. So we just like say in this way. So we just say like in that case. So whenever we'll be like dealing with height, so we'll be always starting with two leaf nodes. So let's say this is the leaf node, this right here, and this is also the leaf node. So they both are at the height of 0 because they are the leaf nodes for this particular tree. And similarly, this node is the leaf node, so the height of that leaf node is 0. Now this node is not a leaf node, even though the level of these two nodes you will be seeing that it is as same as this, but they are actually not. This the node here will be not present here actually in like imagining the stuff. It will actually be present at the level of this. So you can just imagine in that way. So this node is having the height as 1 because it is at the level 1 and it is not the leaf node. And similarly, this node is at the level 2 from bottom. So like level 0, level 1 and level 2. So this is the height 2 of this particular tree. So this is how we actually like calculate the height of this trees. We'll be coding it out in like few minutes after this presentation. So like everything will be clear in that scenario as well. Now coming towards this D. So D was nothing but the depth of the tree. So whenever we see depth, we just go down. So depth is nothing but going down in a tree. So what we can see is this root node is nothing but a depth zero, because it is the starting point. As the starting point was the leaf node for here, so they were at the height of zero. So similarly, we have this at the height of depth of one. So you can see this as a depth of one because they are just one node, one we can say level down from the root node. Similarly, there this two nodes, which is at the, let's say, the bottom or the leaf nodes for this particular tree, they are at like, let's say, 1 and 2 depths away from this root node. So hence depth for this particular node is 2. So you can see like 1 right from here to here, and then 1 from here. So this 2 is the depth for this node, which is the leaf node, and similarly this 1 and this 1. So this 1 plus 1 is 2. So this is how this depth is actually implemented, and how it's actually like calculated in terms of a tree data structure. Now this tree data structure can be as complex as you can imagine, and so like it's not like this simple one is shown here. So it will be similar to that. It can have multiple nodes. Like this root node can even have hundreds to thousands of nodes, and then like child can have more than that also. So then this way the tree data structures are implemented and are designed in that way. And I would just like to add one thing. You will like you will be have heard of this data structure as graph. So let me just say one line on it. Like graph is nothing, you can say, and graph or trees are very much related because all the algorithms which we study in graphs is also applied in trees. So trees are nothing but a special graph, you can say, wherein there is no cycles present in it. Like if I just add a edge from here to here, then this particular tree will be like converted into a graph, you can say, because we have a cycle here. So what does that mean? It's like starting with one, I can again reach to one. So 1, 2, 5, 3, and again one. So this is nothing but graph. So what is tree? Tree is nothing but the special case of graph where we don't have any cycles. So this is the like term which is very much related to each other, because I've seen many of my friends even like they are confused between trees and graph. So this is the basic thing. So now there are different types of trees present. So first one is binary tree. So binary tree is nothing. It is like we have this node and we will be having just, let's say, the two children of it. So it's like binary. So binary means two. So basically this is it like basic example. So we'll be having a node and each node will be having two children. Similarly, this node will be having two children like this, and similarly the this node will be having two children like this. So this is nothing but a complete binary tree, you can say. If like I would have not drawn this right here, this two children, then it will be an incomplete binary tree. It will still be a binary tree, but it will be an incomplete binary tree, because the child, you can say, is one child is having at the same level the two children, and the another child of parent node is not having. So it is incomplete binary tree, and this is the complete binary tree. Now what is this binary search tree? So it is also binary tree wherein all the properties of binary tree is satisfied in it, but it also have a special property of sorting the elements. Basically what it does, it stored elements in a sorted order. So let's say I have added 10 here. So whenever I'll be inserting 5, it will be like comparing it. So 5 is less than 10, so it will be like inserting it here, not on the right side. So all the nodes in the left side will be having the values smaller than the parent node, and all the node to the right side will be having the values greater than the right node. So this is what we term as binary search tree. And why it is important? It is important because we are actually calculating anything or searching anything in log n complexity. Because if you compute the height of this binary search tree which we built, it generally it is log n, where n is nothing but the number of nodes. So now this is AVL tree. This is quite interesting. So AVL tree is nothing. They all are actually linked. So AVL tree is nothing but self-balancing binary tree. Now what does that mean is, in this binary tree, let us say that you will be having more nodes over here, and similarly this node will be having a children, and similarly this will be having a children. Okay. So this AVL tree, what it does is it does not allow this type of structure, as it will disbalance, you can say, the binary tree which we have built, and the height will not remain log n. So what this AVL tree has speciality is it will self balance itself. So whenever you say, let's you inserted we want to insert 2. So whenever it will see that it is not balanced binary tree, so it will try to shift this particular nodes in such a way that after shifting it, it will be become balanced. Balance in the sense like this binary tree will not look like this. So it will something like after reconstruction, it will be looking like this. So this is what the AVL tree will or will be having a speciality about it. And we have many more trees like red black trees. Even in competitive programming, we generally use this segment trees, Fenwick trees. So yeah, we have many trees, but that is it about trees or different types of trees. Now we'll be like seeing some applications. Applications are very common of this because tree are something which is vastly used in our databases. So whenever you have used this MongoDB, so MongoDB is vastly using tree data structures. So you have that document type model. So what document is? Document is nothing but the node of every tree. And whenever you are querying anything on database, it is just fetching that in a login time, you can say. So that's why MongoDB is really efficient and it's vastly used. So this is the major like the application of tree which I've seen also. So apart from that, like we use heap. Heap is a kind of tree where we using the heap sort. We have this sorting algorithm where we use this heap kind of tree where heap is nothing but the max heap and I mean heap type of tree. Where just a second, yeah, where you'll be like storing the maximum element at the top of the tree, just as we hear. So in this tree, this node will be like giving the maximum element, so that will be termed as max heap, or this node will be giving the minimum element, so this will be termed as min heap. This is also quite interesting data structure. So like this is this about application of heap, and you can see like the compilers use a syntax tree to validate the syntax of every program. So yeah, you can do this problem using stack also, but why tree is efficient is we know because stack has limited amount of space which we have to define it while writing our program. So that's why we prefer trees. So we can use trees for like syntax stacking and everything. And most important thing about trees is this tries. So tries are nothing but it is a version of tree wherein we just store, let's say the if let's say this is the tree, then we'll be let's building like you can see, I will like to just throw an example so that it won't become too complicated for you. So we have this contact list in our like in our mobile phone. So we have many contact lists. So whenever like we want to search in our phone, like any contact list we want to search. So what I do is it do nothing. What it do is it has stored this contact list or the contact name in the form of tries because many of their contact name matches. That's why they are sorted in alphabetical order, and you can find many names starting with the same letter. So what they thought is they have built the try data structure out of it, and then whenever you query or whenever you type something in the search box to just say like find any contact, then the search box will be returning query very fastly. Like you have seen like while typing the contact name, you are getting the results even if someone is having thousands of contacts in this phone. If you try to implement this particular algorithm by yourself, you will like by using normal data structures like arrays, linked and many others available, and it will be very slow as compared to tries. So this is what I loved about the tries and heap. That's why it's like I would like to mention that. And like now going on to like actual coding of trees and like how we'll be implementing trees. So I'll be using C++, or you can say like similar to C is like I'll be just using C and C out. So I'll be using C++ to code out actually the tree data structure. So you can see on the left side I have this. So this is nothing but the actual code of this thing which is present here. So a node is nothing but a data which will the value which is stored in it, and it will be containing a left pointer or left reference which will be like storing the reference to next node, and then we'll be having the right reference which will be storing reference to right node. So this is how we will be defining it in code. So this data will be containing this data. The left pointer is nothing but this left pointer is nothing but the left reference for this thing, the next node, and right pointer is nothing but the right reference to that particular code. So that's the basic thing for trees. Now let's jump into coding because here is not something which I also love, but something or sometimes we need to like look into some theory. So I'll be just opening my VS Code. I like if you like to ask anything till now, then you can just ask in your query. Let me see the chat. Yeah, you can ask in your query because we'll be just starting out for coding. Until then, like if anyone wants to continue to code along with me, they can because that will be actually the most appropriate way of taking learning from this meeting. So yeah, any questions till now? I'll be continuing in like 20 to 30 seconds if I'm not getting any question. Till then, like you can just switch on your PC, or if you're joined to your PC, just open up your text editor or wherever you code so that we can code along. Okay, so I'm getting as no questions. So I'm assuming everything is clear till now because that was some basics parts about. So I thought let's cover it, and because everyone will be actually knowing what does that mean. So let me just open it. Yeah, so I guess many of you would have opened up your text editor or the compilers where you write the codes. I'll be just opening it. Yeah. So firstly, I'm like, as I said, I'll be using C++. So just the thing is, understanding the core logic is important because coding out in any language is nothing a big deal. It's not like I'm a big fan of C++, but while doing CPU, we generally use C++ because that is the preferred language of so-called CPU guys. So that's why I'm also using it. So I'm just writing the basic things which we need to write for a C++ program to execute. And then I'll be writing the things which is actually required by us. So this is the basic thing which is required. So I've just defined the long integer as integer value, as a LL value. It is a short form for it. So basically I'll be using that. So as I said, this is the node, which is basically the node which we'll be defining in our tree. So we'll be using so-called structure, which is a part of C and C++ for defining that node. So let's start. So I'll be defining a structure whose name will be node, and then we'll be having, let's say, a data value in here, and then it will be like containing a pointer. So pointer or reference. So for storing reference in it, we just need to, say that which type of reference you need to store. So I'll be just storing the node type of reference in my left node, and similarly I'll be just storing the node type of reference in my right node. So these two are basically the reference which I'm going to take as the left node and for the right node. So this is nothing but, you can say, the actual data for our node. This is nothing but the mm, left reference or the next node reference in simpler or simple words. Next node reference, you can say. So this is the basic, like, the terminology of tree data structure, or the structure which we'll be using for tree data structure. So we'll be having this as a, like, the initializer in our function, which will be like taking in the new data whenever we'll be creating new node. This method will be called, and then it will be like initializing this thing which is present in our class. So data will be initialized to new data, and then we'll be having this class or this particular structure, left node or is equal to the right node, and they both will be initially set to null because initially we won't be having any node present in there. So this is how the simple structure of a tree which will be used or using in this definition. We'll be not going to how a graph like tree is stored. As I told, like, tree are the special case of a graph. We'll be actually using the simple structure of tree to store a tree, because this is how you will actually learn about tree data structures, and like will be really good in it. So this is definition as I've told you. So we'll be like moving on to traversal technique. So like we have built these trees. Let's say this is the tree. Okay, let me just bring it on. So this is tree. Okay, let me just clear it out. Yeah. So we have this tree. So how will be traversing? Like if we will be having arrays, then we can just traverse it linearly. Let's say if we will be having arrays like this. So this is the linear allocation of arrays. So what we initially do is we just go to this node, zeroth index, 1th index, and the second index, and then third index, and so on. So we use a simple for loop for that because it is a linear structure, and we can just increment our I or any initializer, and then we can just move on to it. But in tree or graphs or any other dynamically data structure or hierarchical data structures, this is not the case. You don't have any, like, direct connection with the integer multiplication of this or something like that. So you have to use something called as pointer traversal. So what we'll be doing is we'll be just starting with this node or placing a pointer at this, and then we'll be just using this left pointer reference. We'll be going to this left node. We'll be just going to this left node and printing out this. And then using this left pointer reference, we'll be just going on to this and printing out this. And similarly, using the right reference of this node, we'll be going out to this. And as you can see, there is no left and right reference here, so it will be null. So we'll be returning here. And similarly, we have done printing this and this. So we'll be returning here, and similarly, we'll be going through right reference and then going on to this node and then printing it and similarly returning it. So this is the basic, you can say, how actually the traversal is done. So while I was saying the things, you can see that I have repeated many things. What I have repeated, repeated the things like I'm on this node and I'm going to see the left reference and will go on this. I'm on this node and I'm going to see the right reference. Similarly, I will see the right reference. So whenever there is a repetition in our coding, or where we say that we are repeating actually the algorithm many times, we generally use like we generally use many things, but you can say we use recursion, this type of thing. Whenever we are repeating our algorithm in itself, so we use recursion. So why do we use recursion? Firstly, because recursive algorithms are a base for dynamic programming, which is quite a huge terrain out there. But it is very simple thing if you like start it from very basics and then go in deep. So yeah, apart from topic, so this is how a tree traversal is done. So we can do tree traversal in basically three ways. So first way is, you can see, pre-order traversal. So what we do in pre-order traversal is first we go to parent node and then we go to child node and then we'll go to right child. So this is the tree or typical tree example. So you can see this is the root node of this tree. Okay, just let me know if I'm going a little fast or so, anything you like to say, because I'm assuming that I'm in right flow and like you're understanding the things which I'm saying it to you. Yeah, you can just stop me. It's not like I'm speaking and you cannot stop me. I'll be happy to help anytime. So I was on pre-order traversal. So this is the root node for this particular tree. So what we do in pre-order traversal, we, as I mentioned here, first go to parent node. So left child and right child. Similarly, in order we'll be going through this. In post order we'll be going through this. So like how actually this naming is done is basically in the reference of the parent node. You can see I've highlighted this. So that's the reason for that was simple, because in pre-order traversal you'll be first going on to parent node. That's why it is like mentioned first in order traversal, and the left and right are in the sequence. They will be like left and right always. So in order traversal, you will be like going to left child, and then in order, basically you will be like middle, you'll be reaching out to parent node, and then you'll be like reaching out to right node. Or what will be the post order? Post means afterward basically, and pre means like before. So before like parent node, and in order means in between. So in post order, you'll be like going to the parent node at last. So this is how pre-order traversal is in simplified way displayed here. So in pre-order traversal, first let's go to parent and then left and then right. So this is the node. So parent of node is node itself. So we'll be just printing out this. So as we have printed 10 here. Okay. So I'm just dry running this algorithm of pre-order traversal. So it would be better for us to actually implement it, because what I'll be writing is the recursive logic for it, and for understanding recursive logic, we just need to like listen everything carefully, which I'll be saying from right now. So as we are doing pre-order traversal, let me just highlight it. We are doing this. So while doing this, what I told is we'll be going to root node or parent node, and then the left node, and then the right, or like right child. So the root node or parent node is 10, which is being printed. Now for this particular tree, this entire tree present here, this entire structure is basically the left child. Okay, for this particular node. And similarly, this entire structure present over here is the right child. Okay, I'm not talking about node, I'm talking about child. So this particular right tree is actually the child for this node. So in pre-order, we first go to root node, which we already have printed, then we'll go to left child or left subtree for this particular tree. So basically, in like this is tree in itself, this is a completely new tree, you can say now. So for this new tree, this will be a root node now. So for this root node, as we already are on a parent node, so we'll be just printing it out. So we have just printed 2. Now for this particular node, this node right here is actually the left subtree, and this node right here is actually the right subtree. So we'll be just going on through left subtree and then just printing out it. So you can see like after 12 we have printed 3. Now as we are doing pre-order traversal, so we'll be just going through parent node, left, and then right child. So as there is no more left child present here, we'll be like returning it, and then we'll be like moving on to the right subtree for this particular child. So now we'll be like printing out this tree nodes tree which is present here. For this node three trees, this will be the root node which will be there. So for this root node, we'll be just printing out the root node as we are doing pre-order. So root will or parent will come first. So this is parent, so it is first printed, and then we'll be moving on to left child. So left child is nothing but 6, so we'll be printing 6 here. And similarly, there is no more left child or subtree present here, so we'll be returning, and then we'll be moving on to the right subtree. So there is only one node in the right subtree, so we'll be printing out that value. So we have printed that value, and similarly, we'll be returning from this tree till here, and then we'll be moving on to this right subtree, and then we'll be printing out this right subtree. So how will we printing? We'll be moving or printing it in the same way. So first we'll be reaching to this root node, and then we'll be seeing that there is a left subtree present. So we'll be moving on to left subtree. So 5 is printed, and then we will be like moving on to this 11, which is the left, you can say, the subtree for this particular tree, and which consists of only one node. So we have printed that, and similarly this after completing the left subtree, we'll be moving on to this right subtree, and we'll be printing out this. There is, as there is no left node, we'll be just printing out this right node. So this is how a typical pre-order traversal on a tree looks like. So I would like to just add one thing here. While I was saying the pre-order traversal, or as I traverse or dry run through it, we have seen that I'm actually repeating that procedure. What I'm doing is I'm just, when I was at the root node, I just move on to the left subtree. Okay, and whenever I was on the left subtree's root node, I also moved on to the left subtrees again. So similarly, I just moved on to the right subtree. Similarly, when the left subtree is done, while pre-order traversal, I just move on to the, let's say, the right subtree. So this is repeating in itself. So whenever we see this way or this type of things, they are actually recursive in nature. They actually have the same way or the same nature. So what we solve is we solve this recursion and high recursion DP problem. So as we have seen that this field is recursion. So what we'll be doing is we'll be reaching to our root node, we'll be just printing out as we have done here. And after printing, we'll be just calling our left subtree, or which is stored in the left reference node. So we'll be calling this this tree out. This it will be again going on to this root node. Similarly, like calling its child nodes. And similarly, we'll after calling the left subtree, we'll calling a right subtree for this particular tree, and the algorithm applied will be same. So let's like code it out the pre-order traversal of tree. So I'm back in my VS Code. I'll be just not returning anything from this particular function because I'm just actually traversing on tree, so there is no need of returning anything. So I'll be just receiving the pointers to root node, or you can say the current node. So why current node? I'm like, I need pointers to traverse on tree. As I told, there is no like array like structure in tree. So whenever I'll be given any problem on trees, I'll be given this pointer to the root node of this tree. So that is what I'll be receiving here. And firstly, the first or the base condition of this recursion is, I'm assuming like you have studied basic recursion. So in recursion, we need two things: the base conditions and the actual recursive calls. Because if you don't include base condition, then a recursive call will be infinite. So that's what the base condition for R is. Basically, this node is null. So there is no tree present, or we have reached to the end of the tree. So if after reaching this root or leaf node, we'll be not having any trees here or like any structure down there. So that's how we'll be like reaching out to our base node. So how we'll be checking that? We'll be just using if condition, and then we'll be checking like if current node is equal to null, that means it is an empty tree. And when it is not equal to null, that means the tree is present. Like this node is not null, that means that the tree is present in its left and right part. So if tree is present in left and right part, so what we do in pre-order traversal is first print out the data in parent node. So let us just print out the data in parent node. So we have this current node, and we'll be printing out data in it. And then after printing on the data in it, what we'll be doing, we'll be calling the left child and right child. So we'll be calling this left subject again, and telling them that do the same thing which I'm done on my particular call. So we'll be just passing the left reference, where left reference is nothing but a pointer to this particular node. So what I'll be doing is I'll be again calling this function, which is basically a recursive call, and I'll just pass the left reference for this particular node. So passing your left reference is nothing but the reference or the pointer to this root node, which is the root node for this particular subtree. And then similarly, I'll be calling the current node and like pre-order traversal and passing it the left is the syntax right, yeah. So passing it the right tree reference. So after this is done, what I'll be doing is I'll be saying that a recursive function just call the right tree in the same way as I called the left subtree. So it will be calling it in the same way. So that's why I've passed the right reference here, and here I passed the left reference. So this is it. Like this is how the recursive functions are written, and this is basically why I love recursive functions and dynamic programming approaches, because they are simple to actually code but not to understand. That's why it took me some time to actually let us understand the core logic of how actually traversal is done. So let me just build a simple tree for you so that we can just see how actually this particular function is working. So I'll be just creating a root node here, and I'll be just assigning it a new node, which I'm then passing it a 10 value, right? And then in the left child, you can say, of this root node, I'll be having a new node, and then I'll be like, let's take 11 or let's take 12 basically. So in the right child of this particular um, tree, we'll be having one more node, and then let's say we have like 14. So this is a simple tree, and I'll be just calling pre-order traversal and passing the root for this particular tree as I told. So this is the root for this particular tree. So let's just save it and then just see how actually things are working or not on this particular pre-order traversal. So let me just run it and just see. Okay, there is some syntax error right there on line number 15. Okay, this is a structure, so it needs any format. Yeah, so it actually like printing the pre-order traversal for this tree. So the tree which I have built is nothing but this tree. So the tree which I built is nothing but let's say this simple tree. Here we have one node, here we have another node, and here we have another node. So this is the simple tree which I have built, and here I have just passed in the 10, and here I have passed in the 12, okay, and here I have passed in the 14 value. So this is the simple tree which I built, and the pre-order traversal will be like parent, left and right. So 10, 12 and 14. So this is the pre-order traversal which we have written and which we have constructed and like tested. So let's move on to in-order traversal. Now, as I've explained you pre-order traversal, it won't take much time for me have to actually explain you this in order traversal because it's quite easy now for understanding. So in order traversal, we have this parent node in between. So left child, parent node, and right child. So we are dealing with this now. Okay. So in order traversal, I said like left child, the parent, and then the right child. So whenever we will be having reference to this as a root node, we'll be moving towards the left child. We'll not be printing this, but this is not a pre-order traversal. This is in-order traversal. So firstly, we'll be printing the left child for this tree. So what we'll be doing is we'll be moving to the left subtree for this tree, so which is this 12. Now as soon as I reach 12, I see that there is one more left tree. So I will not print this because I need to start from left. So I will just be moving on left. So this is the left subtree. There is no tree present here. So this is the data which where in-order traversal will be starting, because this is the leftmost node or the leftmost subtree for this particular tree. So we have printed 3, and then after 3 we'll be moving on to the parent node. So parent for 3 is 12, so we printed 12, and similarly we'll be moving on to the right subtree now, because after left, parent, and then right. So now for right subtree you can see that we have left and right tree. So we'll not be printing this because the just a second. Yeah. So the algorithm says like we need to first print the left node. So left node is 6, so 6 is printed, and similarly the parent node is 4, so 4 and then 7. So similarly, when you will be like traversing through the right side, you will be getting all the required values in the same fashion. So let's just like directly jump into the implementation of this particular thing. So you can see like understand or try to understand or try to recall the things which I just explained you in a pre-order traversal. So in pre-order traversal, what we first did is we just printed out the data present here. But in order traversal, we are first actually moving on the left child, and after that we are just printing out the data, and then we are moving on to the right child. So this is how we will be implementing this. So let's move on to implementation part. So as we have, you know, we implemented in order pre-order traversal. So let me just implement pre-order traversal right here. So I'll be just using the same function definition because that is what a typical tree will take in it so that it can just traverse through it. And similarly, the base case for this is the current node should not be null because if it's null, then it's not actually a tree, and we can just stop in there. Now, first in pre-order traversal, what we did is we just printed out this thing. But in order traversal, we'll not print first because what we want is first the left child and then the parent node and then the right child. So first we'll be traversing on this left child. So we'll be calling first this left subtree, and then again in this left subtree recursive call will be done to this left subtree until and unless we reach the leaf node, and then we'll be returning to the parent of this leaf node and we'll be printing that because this is in order traversal, so left parent and then we will be calling the right subtree. So it's just as simple as that. We'll be just calling in order traversal again and we'll be just, you know, passing the current node left reference here. Now whenever we like reach to the left, we will be just printing out the data present in the left node. So that is what a simple in-order traversal will do. And then once we have printed that data, we'll be just, you know, going to the right subtree for that particular tree. So this is as simple as this. So this is how our in-order traversal will be like. We can say it will be looking like. So as this was a pre-order traversal, so let me just comment it and just call it in order traversal, and we'll be just seeing how actually this is, you know, working while running the program. So let me just run it and see the output for this particular code for in order traversal. So you can see we have got this 12, 10, and 14. So let me just make it pretty so that the output will make sense. So we have this in order traversal, and then we'll be just concatenating. So it, yeah, we'll be just concatenating it. We'll be not printing it on anywhere. So let me just again run it. We'll see the output for that particular thing. So you can see the in order traversal is 12, 10, and 14. So let us just verify. So this was our child, like the tree which we have just built using our code. So in order traversal, we do left, parent, and right. So we go on to this left child, which is 12. Then we go on to this parent, which is 10, and then we'll go on to this right child, which is 14. So 12, 10, and 14. This is what in order traversal of tree this tree will look like. So this is what we have got: 10, 12, and 14. 10, 12, and 14. So this is as simple as that. Only thing is understanding the core logic behind how actually the recursive call is being made, because if you understand this concept, then it will be like big or quite easier for you to understand the graph concepts, which are not actually really easy to understand, which is actually based on this concept. So these are basic traversal techniques. So lastly, this thing is left post on the traversal. So as the name suggests, post, so the parent node will be the last one to be visited. So first we'll be visiting left child, right child, and then we'll be going on to the parent node. So let's say this is the, okay, let me just first erase this all stuff. Yeah, so this is the root node which we'll be getting. Okay, so for this particular root node, as we are doing this thing, post order traversal. So for this post order traversal, we'll be going on to like left node and right node, or left child or right child, and we'll be just moving on to the parent. So for this particular tree, the left child is this, but we'll not be printing this because this is not just the left child. So we'll be going on to this. We can print this because there is no subtree present to the left. Yeah, to the left of this tree. So this is printed. 3 is printed. So this is how 3 will be printed, and then we'll be like going to this root node the parent for this, but we'll not be printing this because in our previous case we were printing this. You can see 12 was printed, but in this case we'll not be printing it because we will be executing or printing this particular node value at the last. That's why it is termed as post order traversal. So we'll be calling this write subtree, and then in this write subtree, this will be the root. So we will not be printing root. We will be just first printing the left node value, then right node, and then root. So 674 will be the post order traversal for this particular write subtree, which is this. And then we'll be like recursive call will be returning to this particular node, and then the 12 will be printed. So this is how the left subtree would actually be printed or be recursed or be like called and just printed on the console. So in this similar way, you can just dry run on this write subtree and you'll be getting this output as expected. Because whenever you will be reaching this, you'll be reaching here on 5 and you will be reaching out to the leftmost node, which is 11, and similarly with 8 to 5 and 10. So 8 to 5 and 10. So this is how the post of the traversal is done. So let's like move on to the logic and then code. So in post order traversal, we'll be calling left child, right child, and then the parent node. So let us just complete this function too, because this is the last browser technique, which is quite common. So let me just write it, post order traversal, and we'll be just taking the reference as we have taken this references above of the node, or let or we are calling it as the current node because that is most appropriate name for it. So we will be first checking that if current node is actually not equal to null, that means it is actually a tree and not just a null value. So we'll be just doing what we'll be doing, we'll be calling left child and then right child and then parent. So we'll not be printing anything. We'll be just recursively calling this function again, and we'll be just telling that a post order traversal just travels on the left tree, and then similarly again we will be calling this post order traversal, and we'll be just telling that hey post order traversal just travels on the right tree. So after traversing on both like left and right, we will actually be printing the parent data. So we will be like going here, we'll be printing this, then we'll be traversing on this tree, and then we'll be actually printing this data. So this is recursive in itself. So same recursion logic will be applied on this, and the output as we did the try run will be generated. So we will actually be printing this data. So this is how we print usually, and then we'll be just saving it, and then we'll be just seeing that it actually is printing what is expected or it's printing something else. So let me just comment out that thing, and then let me just use this function on directly. So this is the post order traversal and I'm just passing the route out there. So let me just plot up my terminal. So let me just run it and see the output which this particular code is given or giving. So it's giving 12, 14, and 10. So let us verify it. So this was our tree. Okay, so this was our tree which we basically wanted to do the post or the traversal on. So the left and the right and the parent. So left child for this tree is 12, the right child is 14, and parent is 10. So the order for the post or the traversal for this will be 12, 14, and 10. So are we getting 12, 14, and 10? Yes, we are getting 12, 14, and 10. So this is like the perfect function or the perfect three functions for writing this different tree traversal techniques. So pre-order traversal, in-order traversal, and post-order. In pre-order, the data will be printed firstly, then we'll be recursing on left subtree and then similarly right subtree. And in order, we'll be like printing data in between of the traversal. So first we'll be going or traversing on left tree, we'll be like printing the data, and then we'll be recursing on the right. And then post on the traversal, we'll be printing out data at last, basically printing out the current nodes data at the last. So we'll be recursing on left tree, recursing on right tree, and then we'll be printing out the data which is being present on that particular node. So this are the basic, you can say the tree traversal techniques which we usually follow while traversing on trees. So as our flow goes, so after basic traversal, let's first move on to this three questions. We'll be basically solving this most probably if we have that much time. So I was actually going to include one more question, but that was a bit of a graph type question, so that's why not included. So firstly, like we'll be finding maximum depth or height of a tree. So what is this actually? So we'll be not like learning anything new to implement this. That's why I just picked those questions which are like quite frequent to be asked and which are related to the concept which we have just studied. So what is maximum depth or height of a tree? So as I have mentioned here, let me just open that slide. Yeah. So in this slide, we have just calculated this. Okay. So this particular thing we have calculated. So that concept is nothing but we'll be starting with root node and we'll be assuming it as a depth at 0, and then we'll be moving on to the child nodes and similarly to its child node, and the depth will be increasing, so on and so forth. So this is actually the depth of a tree which we see. So for this tree, the you can say the maximum depth is 2. Why? Because yeah, let me just clear it because it is not actually clear. So why? Because you can see the depth of this node is 2, depth of this node is 2, so maximum is 2. Depth is 1 also, like depth present for this particular tree is 1, but what we want is maximum depth. So maximum of 1, maximum like 1, 2, and from 0, the max value is 2. So hence the depth for this particular tree is 2. So how will we moving on to implement actually this question? Let's see. This is quite interesting question. You can just think on it, like if anyone can just say out the logic, how actually from the learning which we have taken, how actually we will be like reaching out to calculate the maximum depth. That will be really a nice attempt for this particular thing because we'll be just using that concept, nothing new, nothing else. We are done with the concept studying and then we'll be just solving the interview questions. So if anyone like have gotten any idea, they can just share it, or I'll be just continuing with the explanation of the solution for this particular question. So as you can see, maximum depth is written. So just focus on this thing. So how is maximum depth of a tree is calculated? So the idea is simple. It is just to do a post or a traversal. Now remember this post or a traversal. The word post. The word post means basically we'll be moving on to left child, then the right child, and then the parent node or the current node. So this is what the post and order and traversal is we have studied. And what we'll be doing is we'll be just maintaining the two variables. Now that what that two variables contain is nothing but the height. You can say the current depth for that particular tree will be stored in the left depth variable, or in the right depth variable, the depth for the right subtree will be stored. Now, if we have a tree, let's say we have a tree, let me just take that example only. So we have this tree. So at this particular moment, whenever I will recurse from here to here, okay, to this node, and whenever I will recurse from here to here, I'll be taking the maximum of this two. So maximum of this two is nothing but 2. So it will be returning like 2 from here. So again, it will be like having 2 here. Okay, in that case, so it is like this particular left node or left subtree is giving me 2, and then the right tree will be giving me 1. It's because the depth for right tree is 1. So what I'll be doing is I'll be taking out the maximum of these two values. So this is the left depth which I was talking about, and this is the right depth which I was talking about. So maximum of these two will give me nothing but this 2. So this is how actually we will be implementing this particular logic for maximum depth of a tree. So let's first move on to solving this question, and then we'll be moving to a little bit trickier question of getting the diameter of a tree, and then it's a like a moderate level question of printing nodes at k distance from root. So let's just first start with the maximum depth or height of a tree. So let me just open up this code. I'll be just making this as a short so that we are not actually involved in that currently. Okay, so what function we have to write? We have to get the maximum depth for the tree. So it will be actually returning an integer value, which is nothing but long integer in my case. So let me just define that particular function, which will be actually getting the depth for that particular tree. I'll be passing the root node. As I told, I'll always be requiring uh, a node which will basically be pointing towards the root node or any node. Just I need fetch the reference for that particular tree for my starting of that particular code. So again here, so the logic is pretty simple. Let me just open that again and I'll just give you a brief overview about it. So in here we have this nodes already written. So we can like what we'll be doing is we'll be checking that if the current node is or like the base condition is simple because we are actually using recursion logic. So if the current node is equals to null, then actually the tree is not present. If tree is not present, then there is actually nothing present. So we'll be like returning zero from returning zero value from it. And if actually the tree is present, like in our case, actually the tree is present. So what we'll be doing is we'll be calculating or recursively calling the left tree for this particular tree. Like we'll be calling this particular tree or the left subtree for this tree, and then we will be calculating the left depth for this particular tree. Similarly, we will be like calling the right tree, which is this. It contains just one node, but it can contain more nodes. So this is the right subtree for our main tree, and this is the root node. So we'll be calling this left subtree and getting the left depth for this tree, and we'll be calling this tree and getting the right depth, and then we'll be calculating the maximum of two, because here you can see we'll be getting one. Here you can see we'll be getting not one, we'll be getting two, because two is the maximum value from this. So we'll be getting two and we'll be getting one. So maximum of two comma one is nothing but one. So in that way, we'll be comparing the result of two, and then we'll be like returning the actual value of this particular tree or the maximum depth for this particular tree. So let's move on to code. So we'll be first checking that if we'll be first checking the maximum depth function. So first we need to check if the current value is null. Then if it is null, then there is actually no need to calculate. It is the base case for this. So our recursive function will return from that particular thing. If it's actually a tree and it does not end there and it contains more nodes, we'll be actually getting the left depth for this variable, or let's say the tree, and then you'll be recursively calling this function, and we'll be passing this current node left subtree, which is nothing but this tree, or we reference to this node. So whenever we get reference to any node, we can just traverse on the nodes or the child which are connected to it. So this way, the left node or the left function will be calling it. Similarly, we will be having this right depth, and in that right depth, we'll be passing this current current node, and then we'll be passing the reference to right node. So right node is nothing but the pointer to this particular node, which is this subtree or the traversing this subtree. So this is how actually we will be getting the left depth and right depth for this particular tree recursively. So the problem won't stop here, because we have just got the right depth and left depth, and whenever we will be printing it, we'll be just getting these values as 0, 1, 1, 2, 2, and so on. But we don't actually want that. What we want is we want maximum depth of this particular tree, which is our main concern. So understanding this concept will also help you understand the problem, which was finding the diameter of tree, because we will be using this recursive function in that particular function for calculating diameter of a tree, and that is very much common question for, like, if you did any interview experience, which is of good DSL go round, so they generally first start with this basic questions only. So if you're good with basic, then you can do like anything you want. So if we have left depth and right depth, so our concern is now we need to get maximum value out of it. So we'll be using simple if condition then. So if let's say the left depth we have calculated is greater than the right depth we have, okay, this is the case, then we will be returning what we will be returning. It's common sense. Like if something is greater than that thing and we want maximum out of it, we'll be returning left depth, and we'll be just not returning left depth. Why? Because you can understand here. If like I will be returning left depth from here, it will be actually including this current node. It will be actually including this current node. So I have to include this current node externally, because it will not be included whenever I'm like doing recursive call in left and right part. So I will be returning left depth plus one. So that plus one logic is for that thing, because we are actually not including the current node, and like if this particular left depth is not greater than right depth, then obviously the maximum value is right depth, and same logic for plus one here. So this is a typical function. So for getting the max depth of like a tree which is given to you, so this is how it will be working. So whenever it will be like given a reference to the node, it will be just checking if node is not null, and this is actually the, we can say, the base case for a recursion, which is very much important. If you never forget to write this, then it will be hard to debug actually where your function is not performing well. So it's important. That's why I'm focusing it on more. And then we'll be having like for a tree, we'll be calculating the left depth, which will be actually calling this function itself again, and with the reference of the left subtree. And then again, it will be checking if it is not If it is not null, then again it will be getting the left depth of that particular get depth function, and then it will be calculating or passing the reference to left tree. And whenever this recursive call will return here, it will be executing this particular statement, and it will be performing a recursive calls on right tree, or we will be getting right depth. And whenever we are done with this recursive calls, we in the start tree. So when a recursion or recursive functions are called, they are put in the stacks. So we will be like computing this. So this was actually the core logic. We will be actually comparing the left depth and right depth, and then we will be just returning the corresponding values to it. So like as we have built this simple tree, let me just add something more here so that it actually makes some sense, because it will be not making any sense if I will just run this logic on this. So let me just insert 20 here. So now actually our tree structure is something which I'll be drawing on this board and will be letting you know. So first, let me just call this function. So let us see actually the max depth of tree, what actually it's printing. So let us just call this function and pass in the root here, and then just see. So what tree I have built is this tree. So we were having this tree basically. Yeah, so we were having this tree. So in this tree, let me just make it clear because it's not now. So yeah, so in this tree, we were like this is the basic tree which we initially built. So now what I have done, I have just added the one more left node here and just given it a value of 20. So this is the tree which actually we will be working on. Yeah, you can assume this here it is 20 because it's quite hard to write it. So this is 20 right here. So you can see this is the tree which we are actually building here with our code, and we'll be just getting the max depth, and let's just see the output for that code. What actually it gives. So you can see we are getting max depth as 3. So let's just verify is it actually 3 or not. So you can see this particular slide where we have this tree. This tree is basically the same. It's just that I've not added this right node here. So you can just exclude this from here, and just everything is same. So this is the tree which we actually have built this thing, and then we are getting it here. So whenever we are actually calling this function, or you can say, let's actually consider that tree, and then because we were working on it. So yeah, this is the tree which is actually we built. So whenever we reach here, we will be just calling this left subtree and getting the maximum value or the left depth value, and it will be returning to us, let's say, and then we will be calculating the right value and it will be returning 1 to us, and then we'll be returning it here, and then finally we have like 2, and then the root node value is 1, so it's like 2 plus 1, so it is just returning us the value as the test. Here it is considering that as 3, and then we are actually getting that particular depth. So let's just quickly move on, because so let's move on to our next question, which is actually getting diameter of a tree. Now, what is diameter of a tree is quite interesting thing. Let me just glance you through it. So let's just clear it first. It's quite interesting, the diameter of the tree. So let's see this tree or this tree, the left one right here. Okay. So this is the tree which we will be working. So the diameter for this particular tree is the longest path which we can get in this particular tree between the nodes. So what I mean by that is, if I consider these two nodes, this node and this node, okay. So the path, how we calculate path is we count just the number of edges, as simple as that. So whenever I will try to reach from 2 to 3, what I can do is I can go here and 1, and I can go from 1 to 3. So you can see I have these two edges, so the length is 2, basically between this and these two nodes. So can I have like more nodes or another set of nodes where will be the length will be more? Yes, I can have. So which is that node, which is basically this node. So this, if I consider this 4 and this 3, and I just count the edges, so this is 1, this is 2, and this is 3. So maximum of 2 comma 3 is obviously 3. So we are actually getting 3 as the, you can say, the path length or the maximum path length for this particular tree. And there is one more path which is also of length 3. This is 1, this is 2, and this is 3. So they both are 3. So maximum of 3 comma 3 is nothing but 3. So we don't have actually to focus on it. The main concern was to get the diameter. So diameter is nothing but the maximum path between any two nodes. So maximum path is of length 3. So diameter for this particular tree is 3. This particular question is also reframed as
Hello, Vishal. I think there is some technical problem. Just for a few seconds, we will wait, and I think he will join in back again. Uh, Guys, the event is not yet over. The Vishal will be joining soon, and he will be completing the two questions which were left, and then we will end the event. I think there's some technical glitch from his side. That's why he got disconnected. So soon he will be connecting with us and continuing the questions.
oh, yeah, sorry.
Yeah, I think Vishal have joined.
Yeah, I was actually facing some network issue, but it's stable now.
Yeah, okay, no problem. Yes, you can continue.
Yeah, thank you. Okay, so like how much maximum time we have, Rashmi? Because
Vishal, if you could wrap up in max 15-20 minutes, that would be great.
means 4:30 to 4:35, right?
Yeah, yeah, yeah.
Yeah, okay, sure. So let's just move on to where we stopped. So we were actually discussing this problem of getting the diameter of a tree. So I'll be just covering this question and then we'll be wrapping up because the third question was pretty much simple. So that I'll be just explaining the logic and coding is actually the homework part for you. So basically you also need to do something. So let's just move on to understanding the logic behind how we will be implementing this function. So sorry for network issue first. I'm not actually expecting this. So yeah. So the second question which we will be solving is diameter of a tree. So what is actually diameter of tree? I already explained you, and it is also sometimes called as width of the tree because this is quite interesting. I will just like to put some light on it. Yeah. So why it is called width of tree? Like if you just see the top view of a tree, let's say this is a top view. I guess some of you have studied ED and then you actually know what is top view. So this, like, let's imagine the top view for this particular tree and imagine it as a 3D structure. So whenever you will be seeing it from top, then you will be actually able to see the longest path, which is nothing but the diameter of a tree, because this path will be at the leftmost at the leftmost end or the corner, and this path will be the middle, and this path will be at the rightmost. So this will be visible as a three straight line to you, and this the nodes will be visible as the dots for you. So let me just draw it for you guys. So um, this is how you can imagine the top view for this particular tree will look like. So this the node which is at the left is nothing but the 4. You can see here. This is the thing, and the top node is nothing but you can say this. 2, and this is 1, and you will be having one more as 3. Okay, so this is the top view. You see that we don't actually see this node. Why? Because it's actually hidden between these two lines. Okay, which are actually hidden between these two lines. So actually, it is not considering the length of this tree. You can say. So this concept is actually known as flattening of tree. You can say it in that way. It actually involves more concepts, but as a beginner, you can understand it in that way also. So this is actually flattening of a tree. We have flattened the tree, and now if we want to calculate the length of this tree, or you can say the width of this tree, because that will be a more appropriate word. So the width of this tree is nothing but the maximum path length which we calculated, which was 1, 2, 1, 3. Okay, so this was the tree. So it is also, that's why termed as the width of this tree. So this is where most of them get tricked. Now, if someone asks you to calculate width of a binary tree or any other trees, then the people are first confused at what is width. So width is nothing but actually this thing. So I hope that is clear, because it was sounding interesting to me when I was learning some things about trees. So that's why I thought let's share it too. So yeah, we'll be just jumping on to implementing how actually we'll be calculating the diameter. So the basic thing is the number of nodes on the longest path within the two leaves on the tree. So this is the typical definition or the diameter of the tree, which I'm not going to explain here because I already explained you. So let me just go on here, and then let me just start the actual implementation. So what we'll be doing is, let me just erase this out. Yeah, yes. I hope it is not visible and is found. Yeah. So we'll be having this as a root node or the start of a tree. So what we want is, we want actually the maximum length of this tree. So maximum length is nothing, but if I can say you that, hey, there is this Superman which will be getting you the maximum depth for this tree. Okay, let's say the Superman will be getting the maximum depth for this tree, and Batman will be getting the maximum depth for this tree. So if I would say, if I have maximum depth of this tree and maximum depth of this tree, then if I will just add them, wouldn't I'll be getting the actual length, which is the maximum of this, like starting from the left subtree and is going to the right subtree. Yes, this is actually the concept behind diameter of a tree. Is nothing out of the box. It's just as simple. We just have to look at it in a different perspective. So what I did is, I did nothing. I just did calculated the max depth of left subtree. So let's say the max depth for this will be 2. Okay. So because this is the leg depth of this. So it will be 2, something like that. And similarly, I'll be getting max depth of this tree. Initially, it just contains one node actually, but if the tree get more complex, then it will be containing more number of nodes. So you can imagine like in that way also. So it is just continuing this one. And if I'm having max depth of this and I'm having max depth of this, and then I'll be like adding them on, and then just I will be adding this node also, because I need to consider this particular node path, and that is where the recursive logic won't consider it. So we externally have to tell it that I'm doing +1 in the logic, so that we actually won't exclude this node and we get the actual result which is expected from us. So this is how one way. So why one way? Because it is the base case. You can see we have actually total three ways by which we will be actually getting the, can say, the max depth. Max depth is the one way which I just discussed. The second way is the function itself is calling it recursively. So whenever I will be like calling this subtree of this particular node, it will be recursively calling itself, and then it will be actually calculating the diameter for this particular tree. Okay, so I just need to consider it as this particular tree, because sometimes the interviewer or any other question which is quite good, or it's not of like easy or medium level as well, it's of moderate or something more than that, then they will not actually give the pointer to this node. They will actually say that the pointer is not at the root node, the pointer is some nodes away from root node, or they will actually give you the pointer to leaf node and will say that you have to identify in that way, or they will give you some conditions wherein they will not give you the right direct reference to this particular node. So in that case, you have to consider this 2 and 3 scenario as well. So what you will be doing is, you will be actually calculating the diameter again for this left subtree and again for this right subtree. So this 2 is nothing but the diameter for this left subtree, and this 3 is nothing but the diameter for this right subtree. And what we'll be doing is we'll be doing a simple magic. Just ignore my writing because I'm not using file. So yeah, so we'll be just using a simple magic of maximum of calculating maximum of these three numbers, and the result of this three or the maximum of this three will be nothing but the actual diameter which we want from a tree. Now, if you understand the code logic behind calculating the diameter of a tree, then if I make this tree as a graph, okay, if I just erase this all things, and if I'll make this tree as a graph as I also previously did it, and if I will ask now you to just calculate the diameter for this particular graph, so that question becomes a little tricky because you don't have tree here, and this graph is just one way of seeing it. It can be rearranged in a different way, and we can traverse it in like multiple ways because we have a cycle here. We can like go here, and then we can actually have multiple paths between two nodes. But when it was a tree, actually why tree is simple than graphs is this thing only. But when actually it was a tree, we don't have multiple paths to go between two nodes. Like if I say you should go from root let's say node 5 to node 3. Okay. So if I say you will be like going from node 5 to node 3 using the shortest path, you can say. So the path you will be follow will already be known to me. Why? Because there is only one shortest path. You'll be going here and you'll be going here and then you'll be going here. There is no other by any means you'll be going. If you like not following the shortest path, then what will be going? You'll be going here, you'll be going here, again going here, and then it will be the longest path. So I said that's the shortest path. So I already know, but in graph, if I make it a graph, and if I told you to reach to any nodes between any two nodes, then even by like shortest path, like let's I've told you to go from 5 to 1, so you can go like 5 to 1 and due to this cycle, or we say it as a back edge. I'm just sharing graph knowledge because it's connected to 3 and I'll be just implementing the diameter function right away. So you can also go to this path like 5 3 and 1, so you'll be like following two paths. Now I don't know actually on which path you'll be going, so that's why it becomes quite complicated in graph to actually understand the edge cases and implement the things right. So let me just jump on to VS Code and just implement this function. So we already have this magical get max depth function which we just return. Okay. So let me just make a space and then we'll be just writing a function to actually getting the diameter of tree. So get diameter and name it anything. I just have to name it. So I'll be just defining the reference type which I'll be taking, which is nothing but the current node, as we are using this terminology right from start. So we'll be going with this. So we'll be taking this current node and then we'll be just improving upon our logic actually how we'll be uh, calculating the diameter of the graph. So as I told, we will be given the reference to this so-called root node, and then we actually have to traverse to the left subtree, and then we actually have to traverse to the right subtree. So in that sense, so first the recursive call will be made to get actually the left depth of the tree. So let me just implement that. Yeah, this is the base. So first things first, like what we need to check is this is a recursive function as we are following recursive approach. So whenever we'll be writing recursive thing, first I prefer base case, because if you forgot base case and if you think like we'll be covering it at the end, then I think that is the biggest mistake, because like forgetting the base case will make your code run for infinite times and then we'll be getting famous yearly verdict. So we'll not be getting that because we are already covering this base case right here. So whenever the current node is null, so whenever the node is null, that means there is actually no tree present. So we'll be just returning out from there and we'll be passing 0, indicating that actually there is no tree present. So let's just make a variable to actually store the left height, you can say, for that particular tree. So or the left depth, you can say. So I'm just telling that left depth as left height because that is the most appropriate name here. So we'll be using this magical function is defined by us. So it expects a node type of pointer. So that node type of pointer is nothing but the reference to our left node, where this is the thing. So this max step function, I will just ranking through it what it is. We have written it like it will be getting the maximum depth whenever any node is passed to it. So try to imagine in that way. So that particular get max depth will be accepting this particular node as a root node. Like that get max node function actually doesn't know about this tree. So like that function is unaware of like these two nodes as well, because we are just giving reference to this, and we can't like go from here to here actually, because we don't have this back pointer here, something that doubly linked list. We just are having, like, storing it in this direction, so we can just move it this direction only. So that's why whenever we did traversal, we just went into this direction. So this max depth will be getting the maximum depth for this particular tree, and we have asked for which node you have to get. So it will be getting like the for that particular left subtree. So let us again calculate the height for right subtree, because that is where actual magic lies. So we will be getting this current node, and we'll be passing the right reference of that pointer, and we'll be getting the left height and right height, which I was talking about. So we'll be getting left height and right height, and we are actually storing these two things. And now we have this, like I have mentioned previously, we want three max. We will be taking maximum of three lastly. So we are done with first thing. Okay, we have actually calculated the left height and left right height. So I'll not be like calculating here and there. I'll be just calculating in the max function, because that will save for processing. And then we are moving to second case. So what was the second case? We will be actually getting the diameter for the left tree. So let me just define that variable. We'll just give it a short name. So in left diameter, we'll be just calling this get diameter function. So again, we are doing a recursive call here, and we need to pass in a node here. So what node we need to pass here is nothing but the left subtree node. So for left subtree node, we just need to pass the root for the left subtree, which is the left reference of the current node. So current node reference to left. This is what we need to pass to this get diameter function whenever we'll be like calling it again, and then we'll be similarly be getting the right diameter and again calling recursively, and we'll be passing current node right reference. So right reference is nothing but a pointer to this node. So a start pointer to basically right subtree. So this is how we have actually like calculated second thing and third thing. So we have like covered the edge cases for this, and now there is nothing left actually. Okay, I guess, yeah. So these three things we are done. Now we will be doing nothing. As I told, what we'll be doing is we'll be just calling a zero function, which is just maximum function. So it will take this argument, and we'll be returning maximum of it. So as I told, I'll be like adding left height, and then I'll be adding right height, and I'll be adding plus in it, because as I already mentioned the reason. And then we'll be actually calculating maximum of left diameter, and then we'll be actually calculating the maximum of right diameter. So why I have like calculated maximum of this is nothing huge, because this max function is defined for taking two arguments. So basically I'm passing this and again maximum of this. So this will evaluated to actually calculating the maximum of this three arguments which is being passed to that particular code, and then it will be like returning this answer to us, and let's just if it's returning right. If it's not, then we need to debug it, and that is where actual like coding starts, when you actually know how to debug your code, and then we'll be calling this get diameter function, and then we'll be just printing out the stuffs. So let us see if it's working fine. Okay, it's giving previously. So it's running, and it's still running. Let us see why it goes like that. Why it went like that. So let's just glance through our code actually, what we have written and how the things are not happening according to us, because actually like lucky that this happened, because Uh, oh, it's actually calculated. I thought I need to debug it so that you can also see how things are debugged. So yeah, it's just returning this answer, get diameter, and it's just returning the 4. So why 4 it's returning? Because it's just calculating the plus 1 value we have actually like passed in there. So the core logic which I was trying to explain you was this only. You can like manipulate this function according to the constraint given in that particular question. So like sometimes they just count these nodes instead of the paths. So that are nothing just like the plus 1 value for this same, and this is how it like goes for that particular thing. So that is something like manipulation according to the questions, and then it is done in that way. So this was the like the second last question. There was one more question which was like I need to like you can see we are getting 3, which basically is the path length, and if in some question you are given that consider nodes as like the counting length between the two nodes, then that particular logic will be like this above. So let me just move on to final question, which like I will like to discuss with you all. So like printing nodes at k distance from root. So just give me 2 minutes. I'll be just explaining the logic for it. I'm not actually coding on it. Okay. Let me just erase it and yeah, after. So what it means that let's say this is a given tree to you, and the k value which is given to you is let's say mm, 2. Okay. So what it means is printing k like the nodes which are at a distance of k from this root node. So this is the root node which is given to you. So let's say this is at a distance of 1. Okay, we are considering this. So this is at a distance of 1. This particular level, this entire level is at a distance of 1. Okay. Now this as a distance of 2, this entire level is at a distance of 2. So what the output for this question will look like? It will be 3, it will be 4, it will be 11, and it will be 2. Okay, so this is what is expected output for this question. So it's like pretty simple question. It's just nothing. We have learned everything to solve this question, and it is simple actually from the diameter one because it doesn't involve actually the logic building, but it involves actually the implementation thing. How you actually have understood the recursive logic and how you actually learn to manipulate the things. So these are the 3 questions. These 2 are done. I was planning to solve this, but actually, this is simple homework for you. You should love homework. So, there was one more question from my side, which I'm not actually included in this. If you like to give it a try, you can actually. The question is simple. You have to check whether a given tree is a BST or not. So, what is BST? I already told you. Okay. So, BST is nothing but a binary search tree. So used to use binary search tree. So basically in binary search tree we have this sorted order data. So like we will be having the maximum value of this tree left tree on this node, and we'll be having the minimum value of right tree on this node. So basically all the values which are lesser than the current node will be stored in left node or the left subtree, and similar the values which is stored here will be less than this and this, and the values which is stored here will be less than this but will be greater than this. So in that way, the binary tree is built. So you will be given a tree, like let's say you will be given this tree, and you have to tell whether the given tree is a binary search tree or not. So the intuition behind the solving this problem is basically simple. You can just store a reference of previous node, and whenever you will be like calling next node, you can just compare this two. Like here you can see the left node is actually greater than the right node, then it is actually not a BSP. Okay, this is the simple logic or intuition. Coding involves some more things, but this is the intuition behind that particular thing. So I think that's all from my side, and the flow is given. And thank you from my side. If you want to reach out to me, in case if so, you can just note it on your mail or you can connect me on LinkedIn. So that's where I'll be like always like helpful to you. So I'm done with my side. Passionate, right?
Yeah, yeah. Thank you so much.
Yeah. So
So we will be taking some of the questions. If anyone right now in the meet have some questions, they can just put it in the chat box, or else we will continue with the some questions sets which we received before, like when we rolled out the registration form. So the first, till people write down their questions, we will continue with that question set. The first question was the what is the best way to learn the application of trees in the program?
It's nothing like best or worst. It's like how you take the things or the way you learn. So whenever you see any like good problem based on trees, let's say you are giving a coding contest, okay, and let's say you are giving a coding contest in that there is a question and you are not able to solve it because it was based on concepts of trees. So what you will be doing now is like you will be either ignoring that question or other way you will be like learning something new out of that question, or you'll be trying to like glance through the editorial. So the best way which I can like think of it learning a tree is actually problem solving. Like the more you solve, the more you learn because there is less concepts and more problem solving in trees type of data.
Yeah, yeah, surely. So the second question was that recently I got to know that the binary trees are given a special importance during interviews. Why is it so?
Because whenever you see a data in this world is a little bit of a structured type. Like let's say you have an data of employee, then it will definitely be having let's say the ID of employee, the name, and the data which are actually structured. Type. So if we just say that trees are actually not a structured way because a tree can have one node, two nodes, three nodes, thousand nodes. So by saying binary tree, I'm actually restricting the nodes to be having maximum of two chunks. So in that way, I'm actually defining a proper structure for that particular thing. And binary trees are actually, implemented and used in very vast databases and many other things. So the technologies which they work is what they ask you. So that's why they prefer binary trees more. And even not binary trees, they prefer BST most because BST is quite efficient in binary.
Okay, okay, yes. So the next question was, what are some important topics related to tree data structure asked in interviews?
Yeah, also like they actually won't just ask you on trees, they combine these two topics, which is trees and graphs. So like combining these two topics makes really good complex problems. So first question which is like quite good is the given like how you will identify that whether a given tree or a given structure to you is a graph or a tree. So that is a like good question. And some other more questions are there. So you can just visit a website or read a GFG article for actually like noting down all the important concepts because it's not like notable list. It's quite huge, but what I can say, if you are trying to focus on it, just like covering the basics of trees, and after that, just move on to DP on trees and DP on graphs. Because if the question will come from DP on trees and graphs, then it will be become like quite hard to solve actually. So I will just add on like from my perspective, the more importance will be given to these two topics, which are the DP on trees and graphs. So that's it.
Okay, so one more question was there that importance of trees in AI and machine learning, if there's some importance of trees.
It's there actually. It's quite long answer if I like try to give it, but I'll just give a short insight about it. So if the guy is involved in AI and ML, so you have heard about this neural network. So in deep learning, we just build neural networks and we just build a decision trees. And there are various algorithms. Let's say the random forest algorithm, which if the guy is in AI/ML, then he will be or he or she will be knowing it. So what random forest algorithm does is it's actually build a tree. In neural network, we also do the same thing. We also build a tree like structure, and then even we can build graph. But yeah, that's up to the implementation of that algorithm. So yeah, it really holds good importance in AI/ML as well. So that was it from my side.
Yeah, okay, so that's it from our side of the questions. If anyone have any more questions, they can type in the chat box. If not, then we can just end the session. For a few seconds,
Yeah,
we
if
will
they
wait.
just ask, you can just unmute as well because that would be a much better conversation
Yeah, yeah,
rather than wasting time and typing.
yeah. You can just even unmute yourself and ask questions. I I don't think so. There are any more questions, so we will just end it. Thank you so much, Vishal, for joining us. We are grateful that you could spare us some of your time, and I'm sure
Yeah, just
everyone had.
before leaving this session, just I would like to like receive some feedbacks from like the participants side, like how actually was the session or whether they actually like understood 10%, even 2% or not. That's can you just type in the chat the participants present in this meeting, the feedback
Yes,
for this session. Just 2 minutes more.
yeah, sure. Just guys, whatever
Yeah,
feedback you feel like, you can just don't really hesitate and just type it.
yeah, I'm receiving quite feedbacks. It's not like you have to give the positive feedback. If you give negative feedback, then that will be a learning from me. So that
Yeah.
is what I'm expecting. Yeah, I
So if
think,
I could personally
yeah,
give you a feedback, it would be like the concepts
yeah,
were very clear, and you taught really great. Like the flow was really great, but it's just that the at moment there were times where the speed was little too much for the people who are very into the basic might have faced little difficulty. But if you know the concept, then that the flow is great. But for the basic people, I think the flow was little fast. That's it from my side actually.
yeah, yeah, definitely. So I'll be just noting it down and like improving shortly upon it. Okay, I think we are done with feedback. Yeah, I'm receiving some more feedback. Great. It's great to have such sessions with you guys. Yeah, you can continue, Ashton.
Yeah, so see, I'm very sure that everyone had so much to take it back and learn many new things. And so, thank you for joining everyone. And if you have still any further doubts, you can just directly contact any of the core team member. And even Vishal have shared his LinkedIn, so you can also DM him over there. And thank you so much for being here.
Yeah, so finally, I would just like to thank you for like the team of this CodeChef chapter to inviting me for this session. Yeah, thanks from my side for giving this opportunity to as well. Okay, so
Thank you.
I think we are done. Yeah,
Yeah, yeah, yes, yes, sure.
so yeah, thank you guys. Bye bye.
Bye, everyone.